Today it is my pleasure to introduce you to Dr. Xyoli Perez Campos. Dr. Xyoli is a geophysical engineer from the National Autonomous University of Mexico, UNAM. She obtained a master's in statistics and her master's and PhD in geophysics from Stanford University. She did a postdoc at California Institute of Technology, where she has also been a visiting scholar. She worked as a researcher in the Department of Seismology of the Institute of Geophysics at UNAM as well. Her research interest has been broad and has focused mainly on seismic source, seismic structure, and side effects. She has studied the large earthquakes that have occurred in Mexico in the last 20 years and characterized the geometry of the Cocos Plate under Mexico. She served as head of the Mexican National Seismological Service from 2014 to 2021. Currently, she is in charge of the direction of the CTBTO International Monitoring System Division, and today she will give a talk titled The International Monitoring System of CTBTO. So Xyoli, thanks a lot for accepting this invitation, and we are ready. You can start with your presentation.
Thank you very much for the invitation. I feel very honored to be with you. I'm very pleased to be with you today. As I mentioned to Marco before, this is going to be my first full seminar in English in a while. I have given like my research seminar, but this is new to me. So if I get stuck at some point, please, Sebastian, sorry, Christopher and Celine or Stephanie. It was Stephanie and Christopher. Please jump in and help me. So I'm going to go over the International Monitoring System of CTBTO. I'm going to tell you about a little bit about the treaty, a little bit about the pillars of the organization, and then I'm going to talk about the 4 technologies that the IMS division operates in its stations. With that, I'm going to give you a few examples of what we are able to detect and probably encourage you to use this data for future research. So what is the Comprehensive Nuclear Test Ban Treaty, known as CTBT? This is an international treaty that bans all nuclear explosions by anyone, anywhere in the world, and forever. So far, 186 states have signed the treaty, and 176 have ratified it. The treaty was put forward for signature in 1996, and it's deposited in the United Nations. However, not all the countries that are required to sign it and ratify it have done it. So there is still lots of work going on to get all these states encouraged to sign this treaty and hopefully get into force soon. This treaty is an effective way for the nuclear non-proliferation and disarmament measure. It is very important because it's the first step to a world without nuclear weapons. It's non-discriminatory, and we have an intrusive verification system that is the International Monitoring System and the International Data Center. Also, it has a way to verify if a nuclear test has taken place through an on-site inspection. That's the other pillar of the organization. Furthermore, it's based on confidence building, and this is done through consultations and clarification measures where the states are involved. So in terms of what has happened in history about nuclear testing, it started in the 1940s. There were only very few testing, nine of them. In the 50s, it incremented a lot to 291 tests. In the 60s, there were 763 tests, and in the 70s, 609. When I see this number, I get like really shocked on what we were doing to the world. These are some of the major tests or the most significant ones or the ones that we might remember the most. And you can see that here in the 60s, there was a partial test treaty ban where it was all the tests in the atmosphere and on the water were forbidden. And then what happened with that? All the testing went underground. There was a threshold test that said that the work could not have tests larger of 1 kiloton. And then later in the 80s, there were still many tests on the ground and within those levels of yield until the 90s and the mid-90s that finally the CTBT came for signature. And then you can see that after that, there has been only this test that we know of and that we know that have happened because they have been verified by our stations. So we have had only 2 in the 2000s and 3 in 2010, and all of them, I'm sure you know that they are have done by North Korea. So the role of the IMS is, IMS is for International Monitoring System, is to build, certify, and sustain all the monitoring facilities. And these stations or facilities, because it includes also the laboratories, send the data through the GCI, the Global Communication Interface. They send it to the International Data Center, the IDC. And here in the IDC that is located here at the Vienna International Center, the data is collected, analyzed, and distribute the data to the state parties. And also from the data, some products are obtained. Those are mainly event catalogs, and those are also distributed to the states. The other pillar, and it's the way to verify that the nuclear test actually took place, is the on-site inspection. And for that, the inspections are conducted on-site, but this will only happen after the entry into force of the treaty. The other important player here are the state signatories. The CTBTO, that's the organization for the treaty, we collect the data, analyze it, and say, like, this is what we are seeing, but we don't say this is a nuclear test. We cannot say that. What we do is that we send the data to the states, they do the analysis themselves, and they draw the conclusions and decide. So they have the data that we collect, they have the products that we get, and then from the inspections, they will draw their own conclusions if there has been a nuclear test or not, and they will decide what to do afterwards when the treaty has entered into force. So the International Monitoring System, one of the 3 pillars of the organization, manages, operates, and maintains the verification system through monitoring technologies, 4 of them. This is the Seismic, the Hydroacoustic, the Infrasound, and the Radionuclide. So for the Seismic, basically what we are doing with those stations is listening to the underground. And for that, the goal is to install 170 stations. And up to now, we have installed and certified 153. So the difference between installed and certified is that we go install the station, it's operating, but we give it a time to see if it achieved the level of quality and data availability that we are required. And then when we are sure that those conditions have been met, then we certify the station. Then for the hydroacoustic, that is how we listen underwater. And from the 11 stations that are supposed to compose this network, the 11 of them have been installed and certified. We also have a network of infrasound stations that will help us to listen above the ground. And from the 60 stations that are gonna be the total network, we have certified 53. And finally, for radionuclide technology, that's our final check if it was actually a nuclear explosion or probably or another kind of explosion. from the 96 facilities, we have certified 86. And here the difference is that it's not only stations, but it also includes laboratories. So this is the distribution. It's a truly global network. You can see the seismic stations on squares. The red ones compose the primary array and the primary stations, and the blue ones are auxiliary stations. The difference between those is that the primary stations are CTBTO stations, and the blue ones, the auxiliary stations, belong to the states that operate them, and then they contribute the data to the treaty. For example, Mexico has 3 auxiliary stations here, so they belong to Mexico. They are operated by the university, and they contribute the data to the organization. Then the radionuclide stations and laboratories are on circles, and the hydroacoustic stations are on triangles, and the infrasound stations are on hexagons. And the data center, international data center, is here in Vienna. So all these stations, as I said before, they send the data through this global communication infrastructure. They all send the data here to the international data center, and from there, we also use it to communicate back to the national data centers. That means to the states. So first, if we check the seismic stations, this is the global distribution. All the green ones have been certified. The blue ones are stations that are installed, but still not certified. That means they haven't achieved the requirements of operations that we seek. The red ones, we haven't started any work on the installation or preparation, and this one is now under negotiation, and hopefully will become a blue triangle soon. So we have 50 primary stations and 120 auxiliary stations. These 170 stations, we have 2 types of seismic stations. One type is with a single seismometer, and most of the primary stations actually have arrays of several seismometers. Most of the auxiliary stations, they are stations with a single seismometer. So what we take advantage of for these stations is the propagation of the seismic waves through the earth. And for the explosions, we mainly observe body waves instead of observing also the surface waves as we see in an earthquake. So here on the right, on the bottom, you can see an example of an explosion, Chinese nuclear explosion from 93 and 92. And the signal is very different than for this Mongolian earthquake on the bottom. The difference is very clear that you have very strong signals for the explosions for the body waves, while you have very strong signals for the body waves in the earthquakes. And these are comparable magnitudes, so it's not only the different energy that you're getting, but it's actually the difference in the source that you are observing. There are many ways to analyze these different data and to distinguish between an earthquake or an explosion. And one of them is based on the radiation pattern of the seismic waves. So an earthquake, you will have a double coupled force that generates the signals. And that means that you will recreate this 4-lobe of radiation pattern for the body waves. While for the explosion, you will have this outward radiation pattern and isotropic radiation pattern. So you will get this kind of this kind of radiation pattern. So you will see that when you do the inversion of the moment tensor or the focal mechanisms. This is an example, some pictures of a station located in Kazakhstan. This is an array station, and you can see the conditions on some places. We have a variety of different environments for our stations. This is one of the extreme ones. And this is how the different tests for North Korea have been observed in our seismic data. So going from top to bottom on the signals on the left, you have the signal here for the test on 2008, then the 2009, then 2013, 2016, January, and 2016, September, and finally the last one on 2017. They have the same scale, so you can see the smallest one on the top and going to the largest one on the bottom. So the energy released on this test had been increasing, and you have here the table of how this has been increasing actually. Then we have the hydroacoustic stations, and as I mentioned, we have installed and certified 11 of them. And for these stations, we have two different kinds. One is a hydrophone-based hydroacoustic station. So those are the ones on white. That is this HA11 here in the Pacific. Then there's this HA01 here to the southwest of Australia. HA08 here in Diego Garcia, HA04 here in Crozet, and this HA03 here in Juan Fernandez, and this HA10 that I won't remember the name of this one. So, and then we also have 5 stations, H2, H6, 5, 7, and 9, that are located on island, and they are composed of seismometers that are actually looking for the T phase in these stations. One that I know very well is this one in Socorro Island in Mexico. Those are 3 different sites, and each of them have a 3-component seismometer. So basically it works as an array. So these are the 2 kind of stations. On the left is the hydrophone station and the setting, and on the right is the setting for the T-phase station. So for the hydrophone is very interesting because you will have a short facility here with all the communications and computer and whatnot, the power system, and then it's connected through a cable to these other 3 positions where you have a hydrophone that is at a depth that will capture the SOFAR channel propagation of the hydroacoustic waves, and then a surface buoy to keep the hydrophone at the right depth. So this is a very complex, very costly to maintain setting. Then on the right is a more regular seismic station with the sites on land on an island, and this station will capture both the signal that goes through the underground and then also the signal that goes through the hydroacoustic path through the SOFAR channel. This is the detection capability of only those 6 stations that are with hydroacoustic with hydrophones. So you can see the location of the stations, and you can see that with those 6 stations, we have a very good coverage of the whole oceans in the world. So this is some of the pictures of one of the installations. You can see some of the operations. And I decided to also share with you the video of the installation of this station because I think it's super cool. Let me just change my screen here, and hopefully you can all watch it and hear it. Okay, so I hope you enjoy it and see how cool it is to have one of these stations online. And we have 6 of them, so it's exciting to go to these places and have this work done. You can see a lengthier video in this link. When I finish the presentation, I'll copy the link to the chat so you can actually see it. So, of course, we have recorded other kind of activity, not only nuclear test. For example, this earthquake that happened in 2015 in Chile, the station that is here in Juan Fernandez Island recorded both the earthquake and the tsunami. So this is an example of the spectrogram here, the signal here, and then you can see the earthquake and the T phases and the tsunami in the records. Another interesting application that just came out recently is that with the data for the hydrophone of the stations, they recorded how the let me just get this different pointer. Sorry, no, I cannot get it. Okay, they recorded how the whales sing, and they were able to distinguish different whales. So if I'll try to, there. So I hope you can hear the and then they distinguish different sounds and they attribute it to different types of whales. And this is the last one. Sorry. So sorry, I stopped the screen share. Let me just go back. So I found this really exciting and so cool. Also, I should mention that there was a recent publication also using this data from the hydrophone network, where they see also a drop in the noise level during the lockdown. And they attributed it to the less movement of ships on the ocean because of the lockdown during the pandemic, which I think is very interesting as well. Oops, sorry. There. So the third technology is the infrasound stations. They are arrays. They are distributed in the world like this. As I mentioned, blue is fully certified. Green is fully certified. Blue is installed, but still not certified. And we are still need to work on the red ones. We expect to have 60 stations. So for the infrasound, we can also get different kind of signals for different phenomena, for example, volcanoes. And the network, I'm going to present you an example of this. This is how a station looks like with 4 or 8 arrays, element arrays. It depends if the site has a low wind condition or if it has a high wind condition. The aperture of these arrays is of 1 to 3 kilometers. These are some of the locations and some of the settings, depending on the site, as I said, and again, there's a wide variety of environments where these stations are located. So one example of this and of the use of these infrasound stations or infrasound data was the eruption of the Tonga-Hunga volcanic eruption. So all the 53 stations of the IMS recorded the eruption. Okay, there. So here is the signal. It's very interesting to see that it went on and on and on for several hours, actually several days. This is one day, so it was like 5 days that the pressure waves were going around the globe several times. Actually, if you are attending the next Science and Technology meeting in 2 weeks, there's going to be a presentation about this application. Then finally, the fourth technology, the radionuclide stations. This is the only technology that will let us know that, or that will let us verify that the explosion that we are detecting with any other of the technologies is actually a nuclear test. There are 2 kind of stations. One is for particulates and the other one is for novel gas. And this is the distribution of the stations. And you'll see that this the rotated squares that I forgot the name on English. They are particular stations and the squares are novel gas stations. So for example, in this station, we have both capacities, while in this one, we only have particular capacity. And then we have 16 laboratories. Those are the pentagons that you will find on the map. Yeah, for example, here in Uruguay, you have, sorry, it's Argentina, you have a laboratory here. So this is how the station looks like. This is the particle station, and here is the component for the noble gas system. So in general, this is how it works. It gets the data by sampling and measuring the aerosol of noble gas. And then it's analyzed for all the components. And then there is a ray tracing and an atmosphere transport model to see how these particles are gonna disperse around the world. And this network was very useful for the radionuclide Fukushima Daiichi accident. Like the signal for this accident was observed in the US. So like 5 days later than the accident happened. So that's all I have for you today.